Welcome back! In the last video, we discussed what the scientific method is, as well as what independent, dependent, and controlled variables are. In this video, we will begin to delve into the fundamentals of general chemistry and how it relates to biology. We will focus on atoms and molecules while putting a special emphasis on water as one of the more important molecules in biology. Chemistry plays a large and important role in biology, but it can also get quite complex, so we'll try to make this as simple and easy to understand as possible. We'll start off with the concept of an atom. An atom is considered the basic building block of matter. Everything you see around you is made up of atoms. They come in many different sizes and can be wildly different from each other, which is pretty obvious if you take one look at a periodic table. And these give unique chemical properties to whatever they make up. Now, atoms have three main components: protons, neutrons, and electrons. Protons have a positive charge and are located in the nucleus of the atom. Neutrons don't have a charge and are also located in the atomic nucleus. Now, electrons are quite unique as they are much smaller than the other two components and fly around the outside of the nucleus in what is called a valence shell. These electrons fly around to make sure that the atom is in its most stable configuration. Atoms can lose or gain electrons as well, which creates what we call ions. There are two types of ions: cations, which have a positive charge, and anions, which have a negative charge. Take a second to think about what happens to the electrons in both of these scenarios. When an atom obtains a positive charge, would you expect it to have gained or lost electrons? What about when an atom obtains a negative charge? Pause the video and see if you can come up with these answers. When a positive charge is present, that means an atom has lost electrons, while when an atom has a negative charge, it has gained electrons. This is due to the electrons having a negative charge, as I stated earlier. Let's talk more about this valence shell and how it holds electrons. The valence shell is the outermost shell that carries electrons in an atom. You may learn that there is more than one shell that electrons will travel from, but you shouldn't have to know that for this course. Now, this valence shell is very reactive, so these electrons typically want to react with other atoms in order to obtain the most favorable position in terms of energy. You can easily remember the most favorable position for electrons to be in by using the octet rule. This rule basically states that a valence shell tends to be in its most stable conformation when there are 8 electrons in it. So you can find the most stable state by either adding or taking away electrons until you only have 8 in the valence shell. There is an exception to this rule, and unfortunately it's important, so you should also remember that hydrogen only needs 2 electrons within its valence shell for it to be considered full. You'll start to notice that there are a lot of exceptions to rules in the life sciences. It's just something to look forward to during your studies. Alright, so we understand that atoms can attract or repel each other depending on how many electrons are in their valence, with the main goal being to obtain 8 electrons. This leads nicely into the next topic, which is centered around electronegativity. Electronegativity is essentially an atom's affinity to attracting electrons. Each atom has an individual electronegativity, and the differences between them will determine how strong of a bond they make. You can tell how electronegative an atom is by looking at a periodic table. Over on the far right, we see fluorine, which is the most electronegative atom we will discuss in this class. As we keep moving either left or down, the electronegativity of these atoms decrease. The 4 most important electronegativities you need to know are fluorine, oxygen, nitrogen, and carbon. Just understand that the first 3 have very high electronegativities, while carbon's is much lower and actually very similar to hydrogen's. There are also 4 bond types that you should remember that relate to electronegativity: nonpolar covalent bonds, polar covalent bonds, ionic bonds, and hydrogen bonds. Nonpolar covalent bonds happen when 2 atoms with similar electronegativities equally share electrons. The most common example is a CH bond, or a carbon-hydrogen bond. Polar covalent bonds are when the two atoms have a relatively large difference in electronegativity, and so the more electronegative atom will have a stronger attraction to the electrons being shared. This creates a partial negative charge on the more electronegative atom, as well as a partial positive charge on the less electronegative atom. These partial charges are known as a dipole moment. These dipoles can be seen on a water molecule, where the oxygen is slightly negative and the hydrogens are slightly positive. These are stronger than nonpolar covalent bonds. Now, ionic bonds are when a very electronegative atom fully takes an electron from a less electronegative atom, which causes the first atom to have a full negative charge and the other atom to have a full positive charge. Take sodium chloride, or table salt, for example. The chlorine, or Cl, fully takes an electron from sodium, or Na, to create these full positive and negative charges. So now they would be Cl minus and Na plus. This is the strongest interaction out of the ones that we'll discuss. Now, hydrogen bonds are quite unique, and there's a reason I chose to talk about them last. Hydrogen bonds are a strong dipole-dipole interaction. Hydrogen can have its electron easily pulled away from it, resulting in it having its positively charged nucleus exposed. Now, hydrogen bonds are more specific than just a hydrogen bonding to something else. You typically see a hydrogen bond when a highly electronegative element bonded to a hydrogen makes another bond to another electronegative atom with a lone pair of electrons. Take this image, for example. You see these hydrogens bonded to carbon, fluorine, oxygen, and nitrogen. You may be inclined to believe that these are hydrogen bonds since they are in fact bonded to hydrogen, but this is not the case. These are merely covalent bonds. Luckily, we can utilize these bonds in front of us to eventually create a hydrogen bond. So let's work with what we have. If we take the fluorine bonded to a hydrogen atom and bring it near a water molecule, we notice that the hydrogen creates a bond between itself and the oxygen in the water molecule. This happens because the hydrogen's positive partial dipole notices oxygen's negative partial dipole and wants to make a stable and therefore neutral conformation. Remember that this can really only happen with more polar bonds, such as these three covalent bonds, for example. But carbon bonded to hydrogen would not work because it is nonpolar, and therefore it would not create partial positive and negative dipoles that are needed for hydrogen bond formation. Before we move on, I do want to mention one other important interaction you may need to know, which is called dispersion forces, or van der Waals interactions. These interactions involve extremely small induced dipoles that are present in all molecules. Now, you probably guessed that this interaction is extremely weak due to the fact that it's held together by such small dipole interactions, and you'd be right. However, it's also the primary force that holds different nonpolar molecules to each other. These interactions will get stronger as the molecules involved increase in size. So although they are weak, they're also notably important and worth knowing about. Now, that was a lot of information in a really short amount of time, and I'm sure you're getting bored by now. So let's switch gears and talk about the concept of solutes and solvents. A solvent would be a substance that other substances dissolve in. You can think of a solvent as a dissolver. A solute is the substance being dissolved by the solvent. A very common solvent that we'll focus on for the rest of this video is water. Water is considered the universal solvent since it is extremely polar and has strong dipole-dipole interactions which attract other polar compounds. Put in simple terms, polar molecules really like water, while nonpolar molecules want to avoid it at all costs. Another name for this interaction is called hydrophilicity and hydrophobicity, respectively. Hydrophilicity describes a polar molecule and its affinity for water, while hydrophobicity describes a nonpolar molecule and its natural avoidance of water. Now, could you think of why hydrophilic molecules would be polar and hydrophobic molecules would be nonpolar? Pause the video again and try to think about it for a second. The reason is that water is polar, so other polar molecules are drawn to it. A simple way to remember this is that like attracts like. Polar molecules attract other polar molecules, while nonpolar molecules attract other nonpolar molecules. Think about oil and water, for example. Oil is made up of nonpolar hydrocarbons, while water is made up of polar covalent and hydrogen bonds. When you put them in the same glass, they are clearly separated. This is an important concept to understand, as this is utilized in many cellular components, including the cell membrane, which we will talk about in later videos. I think we're about ready to wrap up this section, so let's recap. Atoms are the basic building blocks of matter. They can have positively charged protons, negatively charged electrons, and neutral charged neutrons. The outermost electrons of an atom live in a valence shell, which is in its most stable state when there are 8 electrons present. We discussed the concept of electronegativity and how largely different electronegative values will create polar bonds, while largely similar electronegative values will create nonpolar bonds. This can be shown in many different circumstances, including nonpolar and polar covalent bonds, ionic bonds, hydrogen bonds, and London dispersion forces. Lastly, we discussed the concepts of solutes and solvents, where solutes dissolve in a solvent. We call water a universal solvent due to its extremely polar nature. Water also plays an important role in the concepts of hydrophilicity and hydrophobicity as well, since hydrophilic molecules attract water due to their similar polar nature, and hydrophobic molecules tend to avoid water due to their dissimilar properties. And that wraps it up for this video. We hope this helped. Our next video will be much more specific to biology as we discuss cells and the cellular structure. Thanks for watching.